1982, a Soviet lander touched down on the surface of Venus, opened its cameras, and started transmitting. In that time, it sent back panoramas of a world no human eye has ever seen directly. 30 years later, one of the scientists who had worked on the mission went back to those panoramas, and he pointed to objects in the frames: a disk, a scorpion, objects that, in his words, appeared, fluctuated, and disappeared from one frame to the next. He was not a fringe figure. He was a senior member of the Russian Academy of Sciences. The objects in them are still there. And the question of what the Soviets actually photographed in the minutes before their cameras died is stranger than the answer the headlines gave it. For most of the 20th century, no one had any idea what the surface of Venus looked like. The clouds blocked everything. We had radar maps, eventually, that gave us a rough sense of the topography. But we had never seen it, not in the way you can see Mars or the Moon. The Soviets had been trying to get cameras onto the surface since 1962. Every early attempt failed. So when Venera 9 carried 2 optical mechanical cameras down to the surface in October 1975, no one knew what to expect. The cameras were unusual. They were scanning cameras, swinging back and forth across the landscape, building up a panorama line by line. They transmitted the image as a digital video signal. On October 20th, 1975, Venera 9 returned the first picture ever taken from the surface of another planet. It showed a rocky hillside, sharp-edged stones, a flat, almost layered terrain stretching off toward a horizon that could not be seen because the second camera had failed. One of the lens caps had not popped off. So, instead of a 360-degree panorama, we got a 180-degree view of an alien hillside. A few days later, Venera 10 landed in a different region and returned its own panorama. Same problem. One camera worked, the other did not. But what those 2 cameras returned was historic. 2 black and white views of the surface of Venus. 2 regions hundreds of kilometers apart. Both showed flat, weathered, broken rock. Both showed an environment that was, in some ways, astonishingly Earth-like. Geological, real. The Venera 9 orbiter, meanwhile, became the first artificial satellite of Venus. It carried 2 more linear cameras that took simultaneous images in violet and ultraviolet light, and it performed the first long-term survey of cloud structure and dynamics. From October to late December 1975, it returned 17 cloud panoramas. We had never seen Venus's clouds in motion before. We had only seen them as a still, smooth blank. Now, here is something interesting. Venera 11 and Venera 12 also carried color cameras, but on both probes, every single color panoramic camera failed. The lens caps did not release. The atmospheric pressure pinned them in place. So, for color images of Venus's surface, the world had to wait until 1981. Venera 13 launched on October 30th, 1981. Venera 14 launched 5 days later. They were identical spacecraft, built to take advantage of that year's Venus launch window. After a 4-month cruise, the descent module of Venera 13 separated from the cruise stage and entered the Venusian atmosphere on March 1st, 1982. The descent took about an hour. A parachute deployed during the upper atmospheric phase, then detached at about 50 kilometers above the surface. From there, simple air braking carried the lander the rest of the way down. It touched down at around 7 to 8 meters per second, just east of an elevated region known as Phoebe Regio. The local time at the landing site was about 10 in the morning. The temperature was 735 Kelvin. The pressure was just under 9 megapascals, roughly 89 atmospheres. The ambient illumination at the surface was about 3 to 3.5 kilolux, the same kind of light you might get in an overcast outdoor scene on Earth. 2 optical mechanical cameras were mounted on opposite sides of the lander. They were higher resolution than the cameras on Venera 9 and 10. They could scan 180 degrees or zoom in to a 60-degree window, and they used a rotating set of clear and colored filters. The filter intervals were specific, from 410 to 750 nanometers with no filter, from 490 to 610 nanometers with a green filter, from 590 to 720 nanometers with a red filter. Blue filters were not useful because the atmosphere of Venus is opaque to blue light. Each panorama, transmitted in the tagged image file format, took about 13 minutes to send through the orbiting cruise stage relay. Each image consisted of 1,000 vertical lines with a resolution of 252 pixels per line, of which 211 were the active image. Each pixel was transmitted in 3.3 milliseconds. The cameras started scanning, the drilling arm extended. A small mechanical sampler reached down, took a piece of regolith, and pulled it back into a hermetically sealed chamber inside the lander, kept at 30 degrees Celsius and at very low pressure. An X-ray fluorescence spectrometer analyzed the sample. The result was a class of weakly differentiated melanocratic alkaline gabbroids, a type of rock related to terrestrial volcanic basalt. Venera 14 would later return a similar sample analysis and find tholeiitic basalt, the same kind of rock that forms at Earth's mid-ocean ridges. A microphone on board recorded the first sounds ever captured from the surface of another planet: the wind, the lander itself touching the ground, the pop of a pyrotechnic lens cap removal, the sound of the regolith drilling apparatus. Venera 13 was designed to operate for about 32 minutes. It operated for 127, and during those 127 minutes, on the surface of a world that could melt lead, it took photographs. The panoramas from Venera 13 are unlike anything else in space exploration. They show a landscape of flat, plate-like rocks, slabs of weathered bedrock surrounded by dark, fine-grained soil. The sky is a yellow-orange color, dimmed by the thick atmosphere. There are no shadows exactly. The light comes from a uniformly bright hemisphere of sky, scattered through the depth of the atmosphere. The lander itself sits in the middle of the image, with its instruments and ring-shaped landing platform clearly visible, the drilling arm, the lens caps, the buffer ring. The original Soviet versions of these images were combined panoramas. The clear filter image was used for sharp luminance. The red, green, and blue filter images, which had a poorer signal-to-noise ratio because they were dimmer, were used to add color. The result was the famous yellow-orange tinted view that became, for many of us, the default mental image of Venus. Decades later, the image processor Ted Streak, working from data archived by the Russian Academy of Sciences, returned to the original transmissions and reconstructed the cleanest possible versions of these panoramas. In some cases, the same image had been transmitted to Earth multiple times, both in real time and from onboard digital tape recordings. Combining those transmissions allowed Strike to recover detail that had been buried in noise in the original Soviet prints. What emerged from his reconstructions are some of the most striking images in the history of planetary science. A stretch of ground on a planet hot enough to melt zinc. The rocks are real, the soil is real. The light, the color, the texture of the world, all real. But this is also where the story takes its strange turn. In January 2012, an article appeared in the Russian news agency RIA Novosti. The English headline read, "Life spotted on Venus Russian scientist." A Google translation of the Russian version read, "The Soviet probes may have photographed creatures on Venus." The author of the underlying scientific paper was Leonid Xanfomality. He was not a fringe figure. He was a senior planetary scientist at the Space Research Institute of the Russian Academy of Sciences. He had graduated from Leningrad Technical University in 1956. He had joined the Space Research Institute in 1968. He had designed the radiometers carried by Mars 3 through Mars 7. He had worked on infrared and ultraviolet spectroscopy and imaging on Venera 9 and 10. His Groza sensors on Venera 11 through Venera 14 were the first instruments to detect what was interpreted as intense lightning storms on Venus. He had worked on the Vega mission to Halley's Comet and on the 1988 Phobos mission to Mars. The International Astronomical Union had named an asteroid after him. He was, by every reasonable measure, a legitimate scientist with a long career. The motivation for his new paper, he wrote, came from the discovery of more than 500 exoplanets, many of them so-called hot Jupiters. He argued that we might be guilty of what he called terrestrial chauvinism, the assumption that life can only exist under Earth-like conditions. Many of the newly found exoplanets had conditions much closer to Venus than to Earth. So, if we were going to seriously look for life beyond our solar system, perhaps we should not so easily dismiss the possibility on our own next-door neighbor. His method was to revisit the original Venera lander panoramas. He pointed out that most of the published panoramas were mosaics. Each lander had taken several scans, sweeping back and forth, and the published images were composites built from the best parts of each scan. He wanted to look at those individual scans separately, to see if anything moved or changed between frames. That, in itself, was a reasonable thing to do. What he did next was where the paper began to come apart. In the panoramas of Venera 13, Xanfomaliti identified several objects that he claimed appeared, fluctuated, and disappeared from one frame to the next. He gave them names. The disk, a round, partially cut-off feature at the upper boundary of one image, about 0.34 meters across. The chevron, a symmetrical bright object formed by what he described as numerous angular folds that appeared in a later frame. The black rag, a vertically elongated black object, about 60 to 80 millimeters in size, that appeared wrapped around the conical measuring hammer used to test soil mechanical properties. According to his analysis, it appeared in the image taken in the first 13 minutes after landing and was gone by the 2-7-minute frame. The Scorpion, a roughly 15 to 17 centimeter long object with a complicated structure that, in his reading, resembled some terrestrial arachnids or insects. He claimed it appeared around the 90th minute after landing and was no longer visible by the 119th minute. He proposed that the Scorpion had been buried by soil thrown up during the landing impact and had then slowly worked its way back to the surface over the course of about an hour and a half. The wood fungus, a regular shape with bright spots along its edges, about 6 to 7 centimeters long, that he described as resembling a terrestrial wood fungus. The mushroom, a tent-shaped object about 8 centimeters across, located in the foreground of a Venera 13 panorama, which he claimed was elevated above the surface by about 3 centimeters with no visible support. The animos, a pair of objects about 5 to 7 centimeters long that he claimed were stretched out from a stone in one frame and had moved or bent in subsequent frames. The piles, objects found at the Venera 14 landing site that resembled, in his words, rare bushes on dried-up terrestrial saline lands. The stems, thin, knotty vertical features around the Venera 14 lander, around 0.3 to 3 centimeters thick and up to half a meter tall, some of which appeared to have bulges at the top resembling buds or flowers, and what he described as leaves arranged in a quatrefoil at the base. In total, in the 41 panoramas registered by all the Venera landers, Xanfomaliti claimed to have identified 10 or 11 unusual objects. He proposed that, taken together, they were possible signs of a hypothetical Venusian flora and fauna. The article ended with what he himself called a bold suggestion that the morphological features of these objects allowed one to say that they were living. The story made global headlines. Within days, other scientists and image specialists began their own examinations. And here is where the story turns. Emily Lakdawala, writing at the Planetary Society, obtained a copy of the original paper. she acknowledged Xanthomeliti's reputation. She noted that any paper from a scientist of his standing deserved careful attention. And then she walked through it. The first issue was the bold sentence in the paper itself, which stated that no retouching, drawing in, additions, or adjustments to the images had been made, and that the use of Photoshop had been categorically ruled out. In the very next paragraphs, however, Xanthomeliti acknowledged that adjustments had, in fact, been made. Missing parts of images had been filled in with data from other images. Contrast and brightness had been adjusted. Most strangely, the blur and sharpen functions in Microsoft Windows Paint had been used. Now, blur and sharpen are common image processing operations, but sharpening, in particular, can have very strange effects on noisy images. It tends to amplify random pixel-level variation into things that look like real features. One of Xanthomeliti's own example images showed exactly this. Over-sharpening had produced what one analyst called a ringing of the rocks in the image. A large area of missing data had been filled in with a piece from another panorama. Don Mitchell, who has worked extensively with the original Venera data, has shown that two successive Venera 13 panoramas of the same scene, transmitted using different methods of modulating the radio signal, contain a great deal of difference between them. But it's almost all noise. The two transmissions used different modulation. One was pulse code, the other was pulse time. Each produced a different characteristic pattern of noise. Plotting one image's pixel values against the other doesn't produce a clean diagonal line. It produces a spread, with systematic variations in certain regions. The two photos are fundamentally similar, but with a great deal of noise layered over the top. Then there was the question of what was happening physically at the landing site itself. The Venera landers came down hard. They threw up dust and small soil particles, some of which settled back onto the lander's flat surfaces. Some of that material was blown away in the brief minutes the lander operated by surface winds that moved slowly but acted in a very dense atmosphere. Mitchell, working with the same data, has shown that surface changes did occur from one panorama to the next. Soil was visibly blown away from the landing ring. Lighting changed slightly as cloud structures shifted overhead. In other words, real changes do occur from frame to frame, but they have to do with dust, wind, and the way the radio signal was modulated, not with biology. The most important counterargument, though, came from a closer look at the so-called disk. According to Jonathan Hill, a research technician and mission planner at the Mars spaceflight facility at Arizona State University, higher resolution versions of the same Venera 13 images showed that the disk-like object Xanthomeliti had identified was a mechanical component of the lander itself, specifically a camera lens cap. Each Venera lander carried two cameras, one in front and one in back. After landing, the lens caps over each camera were ejected by spring-loaded mechanisms or pyro cartridges, popping off so that the cameras could begin scanning. Some of those caps did not always release cleanly. On Venera 9, Venera 10, Venera 11, and Venera 12, at least one lens cap on each lander failed to come off, which is why we have only partial panoramas from those missions. On Venera 13, both caps released. They fell to the ground. They became visible in the panoramas. What Xanthomeliti had read as a single disc-shaped object that moved from one frame to another, Hill argued, was actually two different lens caps, each visible from a different camera. One image showed the front camera's cap. The other showed the rear camera's cap. They were not one object that had moved. They were two stationary objects in different places. The same object, in fact, appears in the images from Venera 14. Venera 14 landed roughly 950 kilometers from Venera 13. The probability that, at two landing sites that far apart, the spacecraft would happen to come down within inches of two unique living organisms, in the same position relative to the lander, is essentially zero. According to Hill, it makes much more sense that the half-circle objects are pieces of the lander itself, designed to break off during deployment. In fact, on Venera 14, the lens cap had a famous secondary career. It popped off the camera and landed exactly under the spring-loaded arm that was supposed to test the compressibility of the Venusian surface. The arm came down on the cap. Instead of measuring the soil, Venera 14 measured the compressibility of its own lens cap. As for the Scorpion, Ted Strike, who has spent years reprocessing Soviet space imagery, examined the original transmissions and concluded that the features were not in the original data. They were, in his words, processed noise, at best, in some particularly bad versions of the images. Or, as Hill put it, the image was an example of letting your mind see patterns in low-resolution data that simply weren't real. So the claim collapsed. But what's interesting is what the collapse actually leaves behind. Because if you strip away the speculation, what remains is still extraordinary. The Venera panoramas are still some of the only ground truth images we have of the surface of Venus. They are still, in many cases, the only data we have for the interpretation of all the orbital, radar, flyby, and Earth-based observations that have been done since. The last successful Venera landing was in 1982. The Vega missions of 1985 dropped 2 balloon probes into the night-side atmosphere, where they floated for less than 2 Earth days each before their batteries failed. Since then, no spacecraft has landed on Venus. That is more than 4 decades of silence on the surface. In that silence, the data has been re-examined again and again. Some of those re-examinations have been productive. Ted Strike's reconstructions, working from raw digital data and photographic records, have produced versions of the panoramas with detail and dynamic range that the original Soviet prints could never capture. He converted the logarithmic brightness, encoding into linear brightness. He used the published photometric function of the cameras. He used in-painting algorithms to fill missing regions. The final Venera 13 panoramas in his hands are the cleanest images we have ever had of the surface of Venus. Some of those re-examinations, like Xanthomalites, have crossed a line. The editors of Solar System Research, the journal where his original paper appeared, eventually published an editorial comment, along with several commentary articles from other scientists. A second article from Xanthomalites was also included, in which he claimed to identify additional life forms. One of the more thoughtful comments came from Yuri Gektin, one of the engineers who had actually worked on the Venera television experiments. As paraphrased by Xanthomalites himself in a later interview, Gektin said this: "We do not like the hypothesis that life may exist on Venus, but the problem is that we cannot offer any other explanation to what we see on the Venera panoramas." That is a very revealing sentence. It is not, in fact, accurate. There are explanations for what is visible in the panoramas: lens caps, dust movement, signal noise, modulation differences, sharpening artifacts. The explanations exist. They have been laid out clearly by multiple researchers. But it captures something else. A genuine longing for the data we do not have, for a new mission, for new images, for something more than 41 panoramas from the early 80s. Now, here is the strange part. Even setting aside the question of life, the things we don't know about Venus are remarkable. We don't fully know what the global cloud structure does at all altitudes. We have measured the upper troposphere, between about 60 and 70 kilometers above the surface, where the high-altitude winds reach about 100 meters per second, but the slower atmospheric layers below the clouds remain less mapped. We don't fully understand the polar vortices. Each pole of Venus has a giant double-eyed storm structure with 2 centers of rotation connected by shaped cloud patterns. The first such vortex was discovered at the North Pole by the Pioneer Venus mission in 1978. The second was discovered at the South Pole by Venus Express in the summer of 2006. They rotate with a period of about 3 days. The wind speeds at their outer edges reach 35 to 50 meters per second. The temperature at the cloud tops in each vortex is much warmer than in the surrounding cold polar collar regions. The two-eyed structure has not been fully explained. We don't know what the unknown UV absorber really is. There are dark patches visible in ultraviolet images of Venus that absorb sunlight in ways no identified compound fully explains. Carl Sagan, in 1963, proposed that microorganisms in the upper atmosphere might be the agent. Other candidates have been proposed since. Disulfur dioxide, a substance called red oil, made of mixed organic carbon compounds dissolved in concentrated sulfuric acid. As of the most recent analyses, the composition of the unknown UV absorber remains unidentified. We don't fully know whether there is lightning on Venus, in the conventional sense. The Venera 9 and 10 orbiters obtained ambiguous optical and electromagnetic evidence. Venera 11 through 14 carried instruments to look for it and detected very low frequency waves during descent. Venus Express in 2007 detected Whistler waves, which could be attributed to lightning, with intermittent appearance suggesting a connection to weather. But the JAXA Akatsuki spacecraft has indicated a very low flash rate. And recent work from a Parker Solar Probe flyby has suggested that the direction of those Whistler waves was towards Venus rather than away, indicating a possibly non-planetary origin. We don't know whether phosphine is really there. In September 2020, a study using the James Clerk Maxwell and ALMA radio telescopes reported the detection of phosphine in trace amounts in the atmosphere of Venus. Phosphine is a potential biomarker. No known abiotic process on Venus had been identified that could produce it in the quantities reported. The result was scrutinized. Initial reanalysis identified an interpolation error and produced either no detection or a much lower signal. Later analyses recovered some signal, with sulfur dioxide contamination only contributing a small fraction of the original detection. As of the most recent preliminary work in September 2024, using JCMT Venus data, a phosphine concentration of 300 parts per billion at an altitude of 55 kilometers has been reported. Further data processing is still needed. We don't know whether Venus had oceans. Studies of the present cloud structure and surface geology, combined with the fact that the sun's luminosity has increased by about 25% since around 3.8 billion years ago, suggest that early Venus may have had liquid water on the surface. The runaway greenhouse effect is thought to have occurred around 4 billion years ago. The common view among researchers is that water may have existed for about 600 million years on Venus before evaporating. Some, including David Grinspoon, have proposed up to 2 billion years. The deuterium to hydrogen ratio in the present Venusian atmosphere is 100 to 150 times higher than the terrestrial value, which is interpreted as strong evidence of significant historical water loss. That last fact is, in some ways, the most haunting. Venus has lost an enormous amount of water to space over its history. The deuterium left behind tells us so. Hundreds of millions, possibly billions of years ago, there may have been oceans on the surface of the planet that today is hot enough to melt zinc. That history is locked into the chemistry of its present atmosphere. So when you go back and look at the Venera 13 panoramas, knowing all of this, you see them differently. You see the slabs of bedrock surrounded by fine, dark soil. You see the yellow-orange sky, which is yellow-orange because the thick atmosphere absorbs blue light through Rayleigh scattering and possibly through an additional unknown blue-absorbing gas component. The text color used on Don Mitchell's web pages was, in fact, chosen to approximate the Venera 11 sky color from its measured zenith spectrum. You see the lander itself, the buffer ring, the drilling arm, the two ejected lens caps that, for a brief period in 2012, were misidentified as a living disk. You see a place where the wind moved only a few centimeters per second, but where the atmosphere was so dense that even that small motion could carry dust across the rocks. You see a place where the temperature was 462 degrees Celsius and the pressure was around 89 atmospheres and the air was 96.5% carbon dioxide. And you see a place where, for 127 minutes, a Soviet machine sat on the ground and looked around, and then it stopped. The footage was not buried in any conspiratorial sense. It was archived, studied, and published. But for a long time, it sat unanalyzed in its rawest forms. The reprocessed versions only emerged decades later through the patient work of researchers who tracked down old digital tapes and photographic records and rebuilt the images from the original transmissions. What was buried, in a different sense, was the question of what to do with those images. For more than 40 years, Venus has not been visited on the ground. Vega 1 and Vega 2 inches 1985 dropped balloons into the night-side atmosphere. They lasted less than 2 days. After that, attention shifted to Mars. There have been proposals. The Venus In Situ Explorer, the Venus Mobile Explorer, a long-lived Venus balloon by Global Aerospace, a solar flyer proposed by Jeffrey Landis, designed to operate at an altitude where sunlight, air pressure, and wind speed could allow it to remain aloft for as long as its mechanical components held out. None of those have flown. There is a Russian Venera D mission planned, with current plans for a launch no earlier than November 2029. The aim is to study the structure and chemical composition of the atmosphere, the upper atmosphere, the ionosphere, electrical activity, the magnetosphere, and the rate at which the planet is losing its atmosphere to space. There has been discussion of including NASA components, balloons, a sub-satellite for plasma measurements, a long-lived surface station. There is the NASA Davinci Plus mission, selected in June 2021, scheduled to send an atmospheric probe to Venus in the late 2020s. It will be a descent sphere that plunges through the planet's thick atmosphere, measuring noble gases and other elements to try to understand whether Venus once had an ocean. These are real plans. They have not yet flown. So for the moment, when we want to know what the surface of Venus looks like, we still go back to 4 landers from 1975 and 1982. Venera 9, Venera 10, Venera 13, Venera 14, 2 black and white panoramas from the first 2, 4 color panoramas from the second 2. That is everything we have. That is the entire library of human photography from the surface of our nearest planetary neighbor. There is something quiet about all of this. The footage is not hidden. It is simply old. The probes are not lost. They are simply still there, on the surface, where they stopped working decades ago. The hottest planet in the solar system is still doing what it does. The clouds are still circling once every 4 Earth days. The acid rain is still falling and still evaporating before it lands. The polar vortices are still spinning with their 2 unexplained eyes. The carbon dioxide at the surface is still behaving as a supercritical fluid, transferring heat with a strange efficiency between day and night. And on a flat patch of bedrock just east of Phoebe Reggio, a Soviet lander sits where it landed in 1982. Around it, the dust the engineers anticipated. The lens cap that became a living organism for a moment in 2012 and then became a lens cap again. The slabs of weathered rock. The sky, the color of nothing else. What the Soviets photographed on Venus, before their cameras died, was a real landscape, a real surface of a real world. They did not photograph creatures. They did not photograph life. The most careful reanalysis of their data has shown that the objects identified as a disk, a scorpion, a black rag, a wood fungus, a mushroom, anemones, piles, and stems are some combination of mechanical components, image processing artifacts, signal noise, and patterns the human eye finds in low-resolution data because the human eye is built to find patterns. But what they did photograph and what they did record is more interesting than the claim that has tried to grow over it. They photographed the surface of a planet we do not understand. They recorded the first sounds ever heard on another world. They sampled rock that turned out to resemble basalt from Earth's mid-ocean ridges. They survived long enough to send back enough data that, 4 decades later, we are still pulling new versions of those images out of the original transmissions. And they left behind a question we still cannot answer. Why is Venus the way it is? Was there ever water on its surface? When did the runaway greenhouse begin? What is the unknown UV absorber? Is there phosphine in the clouds, or isn't there? What is happening in the polar vortices? Why does Venus, almost the same size as Earth, sitting next to Earth, lit by the same sun, look nothing like Earth at all? For now, we are still working from photographs that were taken before most people watching this were born. The cameras have been dead for a long time. The data they sent back is still being read. What we know so far is what those 4 landers told us. In the 23, 50, 53, 65, 95, 110, 127, and 57 minutes they each had on the surface. What the data suggests is a planet that may have once been more like Earth, that lost something fundamental, and that has spent billions of years becoming the world we see now. Some researchers believe the question of life on Venus is still open, particularly in the upper cloud decks, where temperatures and pressures are closer to terrestrial values. Others argue that the surface is, by every available measure, beyond what any known biology could survive. What if the next probe gets a longer look? What if a balloon, a flyer, or a long-lived station can stay long enough to see whether Venus is still doing something we have missed? For now, we are still looking at panoramas from 1982, and the more carefully we look at them, the more they remind us of the simplest fact about the planet next door. We have barely been there.